Good day everyone. Today I'll be discussing adaptive metallurgy. So what is adaptive metallurgy? Adaptive metallurgy, a major branch of metallurgy that deals with transforming extractive metals into usable and finished product. Adaptive metallurgy focuses on what happens next, how these metals are processed, shaped, and manufactured into materials and products that we use every day. Before we continue, let's have a quick recap. We have two major branches, the extractive metallurgy and adaptive metallurgy. First, the extractive metallurgy. Extractive metallurgy, this is the process of extracting metals from ores or mineral concentrates. Next, the adaptive metallurgy. Adaptive metallurgy, this is the conversion of extracted metals into usable forms or finished product. In simple terms, extractive metallurgy gets the metal out of the ground, while adaptive metallurgy turns the metal into useful things. Okay, let's proceed to the next slide. What is adaptive metallurgy? Adaptive metallurgy, also known as a metal processing or manufacturing. Manufacturing refers to the making of products from raw or semi-finished materials. This process has existed since the tool age, when early humans began shaping metals into tools and weapons. However, it dramatically advanced during the Industrial Revolution. Specifically, in the second half of the 19th century, when the mechanization was introduced. Machines replaced manual work, making metal production faster, more efficient, and more accurate. In summary, adaptive metallurgy is all about converting raw or semi-finished metals into finished parts such as gears, tools, automotive components, building materials, and countless everyday objects. Let's proceed to the next slide. Classification of metals. Before we process metals, it is important to understand their classification. Metals are grouped into three major categories: ferrous metal, non-ferrous metal, and alloy. First, the ferrous metal. Ferrous metal contain iron. Example na niya kay steel and cast iron. And also, ferrous metal kay commonly used siya for construction, machinery, and tools because of their strength. Next is non-ferrous metal. Kung ang ferrous metal naga-contain siya iron, ang non-ferrous metal naman wala siya ga-contain og iron. Example niya kay copper and aluminum. And also, non-ferrous metal, they are lighter, more corrosion resistant, and used in electrical application, aircraft parts, and packaging. And lastly, the alloy. These are mixture of two or more metals. Example sa alloy kay brass, which contain copper plus zinc. Next, bronze, which contain copper plus tin. And lastly, the stainless steel. And also, alloys are created to achieve improved properties like strength, corrosion resistant, or flexibility. Okay, let's proceed to the last slide. Metal processing and manufacturing. As makita nato sa picture, table 1.1, this table shows various materials used in manufacturing and compares them based on production volume, cost, and density. The first column are material. This column lists the type of material such as iron, steel, aluminum, copper, zinc, lead, nickel, magnesium, tin, titanium, and polymers. Next column is approximate world production tons times 10 raised to the power of 6. This indicates the annual global or production quantity of each material, measured in a million of tons. For example, iron steel has a significantly higher production volume at 768 million tons compared to titanium at 0.1 million tons. Next column is approximate relative cost. This column provides a cost comparison between the materials. Iron or steel is the baseline with a cost of 1, while titanium is relatively expensive at 26. Next column are density, kilogram over cubic meter. Density is a measure of a mass per unit volume. Lead has a high density of 11,300 kilogram cubic meter, while magnesium has a lower density of 1,700 kilogram cubic meter. And last column is approximate volume produced. Cubic meter times 10 raised to the power of 6. This shows the volume of products made from each material. Measured in a millions of cubic meters, iron steel leads with 97 million cubic meters. We need to learn this table because the table highlights that each material has its own strength, production level, and market cost. This helps industries choose the right material for the right application. In conclusion, we need to learn adaptive metallurgy because adaptive metallurgy plays a crucial role in our modern society. Without it, metal extracted from ores will be useless in their raw state. Through processing and manufacturing, we convert them into tools, machine, structures, and everyday items that support our economy and daily lives. It is the field that continues to grow, especially with advancement in automation, robotics, and smart manufacturing.
Magandang umaga, magandang hapon, magandang gabi sa inyo lahat. Ako nga pala si Michael ANTIPALA from Bsem 2A, and I'll be discussing about how raw materials turn into a final or finished products in adaptive metallurgy. So recall that adaptive metallurgy is where our ore concentrates are converted, refined, and shaped into its desirable properties in order for it to be in its usable form. So may dalawang uri ng manufacturing to turn raw materials into a final or finished products. These are primary manufacturing and secondary manufacturing. Primary manufacturing refers to the set of metallurgical processes that convert natural metal ores or ore concentrates into metallic materials or semi-finished metals. So primary manufacturing focuses in which our ore concentrates from extractive metallurgy. Recall that in extractive metallurgy, we extract concentrates away from its ganged minerals through different kind of method like pyrometallurgy, hydrometallurgy, and electrometallurgy. So in primary manufacturing, these ore concentrates are converted into semi-finished metals or metallic materials. While in secondary manufacturing, it is a set of metallurgical and metalworking processes that take semi-finished metals. So yung product ng primary manufacturing and convert them into a usable shape products or components. So let's not delve deeper sa secondary manufacturing since it will be discussed to the next presenter. So let's move on sa mga products in primary manufacturing. So there are two main products of primary manufacturing. These are steel and aluminum, but in their semi-finished form since we're still in primary manufacturing. Ang steel at aluminum ay ginagawa sa magkaibang proseso. Steel for steel making and aluminum for aluminum production. Aluminum production will be tackled by the next presenter, so let's focus in steel. Steel is an alloy of iron and carbon where the carbon content typically ranges from 0.02% to 2% along with the small amounts of other elements. Before we move on the process of steel making, let's talk about the semi-finished forms of steel and aluminum. So semi-finished products are intermediate steel shape produced directly from molten metal during primary manufacturing. So there are four types of semi-finished products. We have ingot, a large rough casting design for storage and transportations. The shape usually resembles a rectangle or square with generous fillet. They are tapered usually with a big end down. Next one is a bloom, a slug-riddled iron casting poured in a bloomery before being worked. into a wrought iron. Further process via rotary pressing, structural shape rolling, and profile rolling. So as you can see sa illustration, so that is a bloom na that when undergo secondary manufacturing, it will turn into a structural shape or rails. So the next one is the billet, a semi-finished length of metal with a square or round cross-section produced through continuous casting, extrusion, or by hot rolling an ingot or bloom. So billet is formed by continuous casting and extrusion of an ingot or a bloom. So as you can see sa illustration, that is a billet, then undergo casting, extrusion, or hot rolling, it will become bars or rods. The last one is a slab. Slab length of metal with a rectangular cross section, typically 250 millimeters or more in width, and 40 millimeters or more in thickness. Further processed into sheets, plates, strips, pipes, or tubes. So again, there are 4 types of semi-finished product: ingot, bloom, billet, and a slab. Then for further process, when these 4 semi-finished product undergo secondary manufacturing, it will convert into a final products like bars, rods, plate, sheets, coils, and etc. So now let's talk about steel making. Steel making is an industrial process in which pig iron from smelting is refined to remove excess carbon and impurities. The molten metal is then adjusted through alloying to produce steel with specific properties before being cast into semi-finished products. So below are the process of steel making. First is smelting, then converting, then alloying. So let's talk about smelting. So way back pyrometallurgy, smelting is where our minerals are being hit above their melting point for us to extract the concentrate away from the valueless minerals. The valueless minerals turn into a slag while the concentrates sink below. So smelting in steelmaking is performed in a blast furnace. The product is pig iron with a carbon content above 3%. Reduction of iron ore to iron with amounts of carbon. So as we all know, other term of smelting is carbothermic reduction, which is carbon in the form of coke or coal are fed into the blast furnace in order to reduce iron oxide into the pure iron. So next, after we have the pig iron, we do converting. So converting is done by Bessemer converter, open heart converter, or basic oxygen steelmaking converter to reduce carbon content up to 0.002%. So as we all know, converting is a process of reducing carbon content and also impurities to achieve liquid metal with less impurities. So after converting, our pig iron now has a carbon content up to 0.002%. Now the last step of steel making is alloying. So alloying is where our pig iron are adds with alloying elements to develop specific mechanical, chemical, and thermal properties such as nickel, chromite, manganese, tungsten, and so on to help our pig iron to achieve its desired properties before being cast into semi-finished products. After talking about the steel making processes, now let's talk about the furnaces that help us to achieve successful steel making in order for us to produce steels. So first is smelting. Blast furnace is used in smelting in steel making. So in this picture, you can see a blast furnace, a large vertical furnace used in steel making to extract iron from iron ore by chemical reduction. also uses carbon as a reducing agent and operates at a high temperatures. So blast furnace works by charging, combustion, formation of a slag, and a collection. So charging is where our layers of iron concentrate, coke, and limestone are added from the top of the furnace. So this is our feeds. Now combustion and reduction happens when hot air is blasted from the bottom, causing the coke to burn and produce carbon monoxide. This carbon monoxide reacts with the iron ore in order for us to get molten iron. Now this limestone reacts with impurities, forming a slag, which floats on top of the molten iron, preventing impurities to mix with our molten iron. Then lastly, collection of molten iron from the bottom of the furnace, while slag is also removed separately. Now let's move on sa converting part. So nasabi ko kanina yung mga Bessemer converter, open heart converter, and basic oxygen steelmaking converter. So these are furnaces that helps our pig iron to reduce its carbon content up to 0.002%. So Bessemer converter is a large pear-shaped vessel used in steelmaking to convert molten pig iron into steel by reducing its carbon content and removing other impurities through oxidation. So charging molten pig iron from blast furnace is poured into the converter. Then a strong blast of air is forced through the molten iron. The oxygen in the air reacts with carbon and other impurities like silicon, manganese, and phosphorus. Then oxidizing them. Then oxidation reaction are exothermic, which keeps the iron molten without external heating. Same with blast furnace. Oxidized impurities combine with added flux like limestone to form slag, which floats on top and is removed. Next converter is the open heart converter. It is a large shallow furnace used in steelmaking to refine molten pig iron into steel by gradually removing carbon and other impurities through direct heating from the hearth and radiant heating from the furnace roof. So as you can see here, this is our open heart converter. Same function with Bessemer converter. It reduces impurities and carbon content of our pig iron by heating. But here there are two types of heating, the direct heating and the radiant heating. So direct heating, burners heat the hearth or the bottom of the furnace, raising the temperature of the molten metal and initiating the oxidation of impurities such as carbon, silicon, phosphorus, and manganese. Then radiant heating, hot gases and flames rise and radiate heat from the roof, ensuring even heating of the molten steel and promoting uniform refining. Then oxidation and slag formation, impurities oxidize and combine with the flux to form slag, which floats on the surface and is removed. And lastly, our basic oxygen steelmaking converter. Same job with other converter. It is to reduce carbon and remove other impurities in our pig iron. So here is a picture of a basic oxygen converter. So molten pig iron from blast furnace along with scrap steel is poured into the converter. Then a water-cooled lance blows a high purity oxygen directly onto the surface of the molten metal. Oxygen reacts with carbon, silicon, manganese, and phosphorus in the molten iron. Carbon then is oxidized to carbon monoxide and carbon dioxide gases which escape. Other impurities are oxidized and form slag with added flux. And temperature control, the exothermic oxidation reactions maintain the molten state of the metal without external heating. So those are the furnaces that helps our steelmaking processes successful by producing a high quality steel efficiently to form our semi-finished product that later on undergo secondary manufacturing to produce our final product. At yun lang at salamat sa pakikinig.
So now let's proceed to the aluminum production, which is the primary manufacturing, the most abundant metallic element in the Earth's crust. its ore is the bauxite, which contains about 75% hydrated alumina, and its process to produce aluminum steel or products is by Bayer process and Hall-Heroult process. So what we can see here is the Bayer process. So above, we can see the bauxite. So ito yung raw material. So bauxite contains aluminum minerals like gibbsite or bomite mixed with impurities like iron oxide and silica. So yung next is grinding. So the bauxite is crushed and ground into very finer particles, meaning to say ginagawang pino ang bato para mas madali itong matunaw sa chemical solution. So, what's its purpose? Its purpose is to increase the surface area and make digestion faster and more complete. So, below the grinding, we can see the digester. Actually, the ground bauxite is mixed with hot caustic soda or like the sodium hydroxide, so under high temperature and pressure. So meaning to say, pinapakuluan ng bauxite sa caustic soda para matunaw ang aluminum minerals. So yung result nito is that the aluminum minerals dissolve, forming sodium aluminate solution, impurities like, and also the impurities like iron oxide, silica, they do not dissolve. Yung output lang niya is a liquid full of dissolved alumina, so meaning the steam hits the digester. So for expansion naman, the pressure is released and the mixture is cooled slightly. So like inaayos ang pressure at temperature bago ito isettle. So its purpose is to stabilize the slurry or prepare it for settling. So for speaking of settling, it is the heavy impurities or the red mud settle at the bottom. So dito bumabagsak ang mga dumi gaya ng iron oxide at iba pang hindi natunaw. So yung two outputs nito is that clear sodium aluminate liquor just sa upper part niya. And the red mud residue which is makikita sa bottom. So for the washing naman, it is a red mud that is washed with water to recover any remaining valuable solution for disposal. So meaning yung hinuhugasan ang mga like mud para masulit ang mga natirang liquid na may alumina. So yung result nito is the red mud ma-dispose siya and the wash water is recycled. So for evaporation naman, water is evaporated to increase the concentration of sodium aluminate. So meaning pinapainit para mas lalo pang lumapot ang solution at like viscous siya ba? Mas mo-viscous siya ang solution para like ready siya sa crystallization. So condensate meaning to steam turned water and it's reused in heat exchangers. So for vacuum cooling naman, the concentrated liquor is cooled under vacuum. So meaning pinapalamig ng mabilis yung gamit ang vacuum para makontrol ang pagbuo ng crystals niya. So the purpose is to prepare for precipitation and achieve correct supersaturation. So for precipitators naman, the small seed crystals of alumina hydrate are added to the solution. So meaning nilalagyan ng binhing crystal para may pagsimula ng pagtugo ng bagong crystals. So yung result nito is alumina hydrate crystals grow. So for liquid, it loses dissolved the alumina. So the step converts sodium aluminate, like for example, sodium alumina hydrate plus leftover liquor. So mga siyang result sa precipitators. So for filters naman, the solid alumina hydrate is separated from the remaining solutions. Siyempre, hinihiwala yung solid sa liquid gamit ang filtration. So yung solid output like is the alumina hydrate and the liquid is the recycled as caustic liquor. While the rotary kiln naman or the calcination, the alumina hydrate is heated to about 1,000 degrees Celsius or 11,000 degrees Celsius to remove chemically the bound water. So like ginapainit siya over para like matanggal ang iyang tubig pag at like para ma-pure siya nga alumina powder. So water is driven off, so yung final product becomes white alumina powder. So sa final product naman is the alumina, which is the pure alumina is produced ready for the Hanna smelting process. So ito na ang like pure na siya nga alumina na gagamitin para gawin ng aluminum metal. So in summary, the Bayer process Firstly, grind the bauxite and the second dissolved alumina using caustic soda and remove the impurities like the red mud, and then eventually concentrate and cool the solution. So after that, it crystallizes alumina hydrate and then heat to produce pure alumina. So actually, this is the world's main industrial method of producing alumina for aluminum. So next is what we can see here is the video of Halherot process. Here, the molten metal will sink to the bottom of the tank and aluminum is collected. So this video explains the extraction of aluminum by electrolysis of alumina. So the electrolysis of alumina is carried out in a steel tank. The hanging carbon block access the anode and the carbon lining access cathode. So we can see it here. Here. This is actually the steel tank hanging carbon blocks access the anode and the carbon lining access cathode. So the electrolyte is the mixture of alumina, cryolite, and fluorspar, as we can see here. And the cryolite lowers the melting point of alumina, and fluorspar increases the electrical conductivity of the electrolyte. So when the electricity is passed through the electrolyte, the alumina is ionized into aluminum and oxide ions. So unlike other charges that attract each other, hence the positive alumina is ionized into aluminum. So meaning to say, it will attract towards carbon lining cathode, and the negatively charged oxide will attracts towards carbon anode and cathode aluminum. So it will gain electrons and form aluminum metal. So sa last part sa video, which is here, it is the molten metal. So eventually the molten metal will sink to the bottom of the tank and the aluminum is then collected. So once the aluminum is being collected, then it is now subject to produce different kind of useful products in our industry, such as the steel and etc.
Hello everyone, I am Mahlon, Rafael, and NERI of Bsem 2A, and I'll discuss the continuation for a group's topic, Adaptive Metallurgy, the secondary manufacturing and metal forming. Secondary manufacturing. Secondary manufacturing in adaptive metallurgy refers to the process of conversion of primary metal products into finished or semi-finished components through various processing routes. Secondary manufacturing takes the raw primary metal outputs like ingots, billets, or cast shapes and transforms them into more refined, usable components. What's important here is that this stage isn't limited to just one method. Several routes can be used depending on the required geometry, material, and application. These processes aim to give the metal its first functional shape before any final treatments or machining are done. Forming methods like forging deform a billet, bar, or powder preform to achieve the desired shape. One major route in secondary manufacturing is forming or shaping, and forging is a prime example. In forging, we start with a solid piece of metal. This solid piece of metal could be a billet, a bar, or even a compacted powder preform, and we apply compressive forces to reshape it. This process not only produces the required geometry, but also improves metal properties by refining the grain structure. Essentially, we're reshaping the metal while also enhancing its mechanical strength. So in secondary manufacturing, the finished shapes are typically heat-treated and finish machined to meet required properties and dimensions. After forming the secondary shape, no matter which route is used, the component typically undergoes heat treatment. This step adjusts the microstructure to meet strength, hardness, toughness, or ductility requirements. Once the desired properties are achieved, we proceed to finish machining. This is where we refine the dimensions, tolerances, and surface finish so the component matches its exact design specification. Heat treatment and machining are almost always the final steps before a secondary product becomes ready for service. So in this flowchart explains the major secondary processing or manufacturing routes in adaptive metallurgy. Let's start at the very top of the diagram, molten metal. So once the metal is melted and ready for shaping, it can follow several possible routes depending on the desired final product, the metal's properties, and the production requirements. One route is directly through shape casting. Here, the molten metal is poured into molds to form near-net shape parts. This is ideal for complex geometries that would be expensive or difficult to achieve through other methods. After casting, the part may undergo joining, machining, or may proceed straight to becoming a semi or fully finished part. Another route is processing into powder, which is used in powder metallurgy. The molten metal is atomized into fine particles. These metal powders then undergo powder consolidation, where they are compacted and sintered to form solid parts. This route is excellent for producing materials with controlled porosity, very fine microstructures, or parts that require minimal machining. Next, we have continuous casting, where molten metal solidifies as it moves through a continuous mold. This process produces billets, blooms, or slabs with excellent quality and minimal waste. From continuous casting, the material typically enters bulk deformation steps such as forging, rolling, extrusion, or drawing, especially for thick or massive starting forms. Another major path is ingot casting, where molten metal is poured into large molds to form ingots. These ingots are later reheated and processed through bulk deformation, again involving operations like forging or rolling to refine the structure and shape of the metal. From bulk deformation, the material may then undergo sheet deformation if the goal is to produce thin, flat products. Sheet deformation includes processes like sheet rolling, stamping, and deep drawing. This is the route used for making products such as plates, sheets, automotive body panels, cans, and other thin-walled components. Many of these processing routes lead to a central step, heat treatment. Heat treatment modifies the metal's microstructure to achieve desired mechanical properties such as hardness, toughness, ductility, or strength. This step is essential because even after shaping, the internal structure of the metal must be optimized for performance. After heat treatment, the metal can follow two main finishing routes: joining, which includes welding, brazing, soldering, or mechanical fastening, or machining, which involves cutting, grinding, drilling, and other operations to achieve precise dimensions and surface finishes. These steps help transform the processed material into a semi or fully finished part. Regardless of the specific path taken, whether casting, powder metallurgy, deformation processing, heat treatment, or finishing operations, the goal of all these routes is to produce a semi or fully finished component ready for assembly or use. Moving on to metal forming. So, bulk metal forming. Bulk metal forming are processes applied to thick or massive workpieces with large or plastic deformation occurs. In bulk metal forming, we work with thick and heavy starting materials like billets, blooms, bars, and large ingots. Processes under this category, such as forging, rolling, extrusion, and wire drawing, subject the material to significant plastic deformation. The operations typically involve compressive stresses, and the metal flows into new shapes with substantial changes in both cross-section and dimensions. This is where we form items like gears, shafts, rods, structural sections, and many high-strength components. Moving on to sheet metal forming. Sheet metal forming are processes applied to thin sheets to create parts with wide surface area and minimal thickness change. Sheet metal forming focuses on thin metal sheets, usually only a few millimeters thick. In these processes, the main objective is to bend, stretch, draw, or shear the sheet into the desired shapes while keeping the thickness nearly constant. Common operations include bending, deep drawing, shearing, stamping, and stretch forming. These techniques are widely used in automotive body panels, appliance covers, aircraft skins, and countless everyday metal products where large, smooth surfaces are required. Now let's walk through the general classification of metal forming processes. This diagram summarizes how all metal forming operations are grouped based on the type and thickness of the material being worked on. We start at the top with metal forming. Metal forming is any process where we deform a metal plastically so that it takes a new shape. Now, this large field is divided into two major categories: bulk deformation and sheet metal working. These categories differ mainly in the shape and thickness of the starting workpiece. Let's look at bulk deformation first. Bulk deformation deals with thick, massive materials like billets, bars, rods, or ingots. These materials have a relatively low surface area to volume ratio, meaning they're chunky. Because of this, bulk deformation processes involve large, significant changes in cross-section. Now, under bulk deformation, we have four major processes. The first one is rolling. In rolling, we pass the metal between rotating rolls to reduce its thickness or to produce a uniform cross-section. This is where we make products like plates, sheets, structural beams, and rails. Rolling can be hot or cold depending on the application. Next is forging. Here, the metal is shaped using compressive forces, usually from hammers or presses. Forging not only shapes the metal, but also improves its grain flow and mechanical strength. common forged products includes crankshafts, connecting rods, gears, and high-strength machine parts. The third one is extrusion. In extrusion, we force the metal through a die opening so that it comes out with a constant cross-section, almost like squeezing toothpaste from a tube. Examples include aluminum window frames, tubes, rods, and decorative profiles. Finally, for bulk deformation, we have wire and bar drawing. In drawing, the metal is pulled through a die to produce its diameter. This is how we produce wires, cables, welding rods, and reinforcement wires. Because the metal is stretched, it also becomes stronger due to cold working. Now we move to the second major category, the sheet metal working. Sheet metal working deals with thin sheets, usually only a few millimeters thick. The deformation here happens mostly across the surface, with very little change in thickness. The first process here is bending. This is when we apply force to the sheet to create angles, curves, or channels. You see this in automotive body parts, brackets, enclosures, and a lot of everyday metal components. Next is deep drawing, also called cup drawing. This is where a flat sheet blank is stretched into a die cavity to form cylindrical or box-shaped parts. A key idea here is stretching, which is even highlighted in the diagram. We stretch the sheet to form shapes like cooking pots, beverage cans, sinks, and casings. Then we have shearing processes. Shearing is simply cutting the sheet without forming chips. So this includes blanking, punching, and trimming. These operations prepare the sheet for further forming or create final cutout shapes. And finally, we have miscellaneous processes. These include specialized sheet metal operations like spinning, embossing, coining, and flanging. They are used when we need surface texture, decorative patterns, or special forms that don't fall neatly into the other categories. To summarize this flowchart, bulk deformation handles thick metals and focuses on major cross-section changes, whereas on sheet metal working handles thin sheets and focuses on bending, stretching, cutting, and surface-based deformation.
Classification of basic bulk metal firming. Bulk firming, it is a severe deformation process resulting in massive shape change. The surface area to volume of the work is relatively small, mostly done in hot working conditions. So basically, it involves severe plastic deformation to change the shape of metals, and it is usually done under hot working conditions where metals have low surface area to volume ratios. The main goal of bulk firming is to produce large shape changes while improving mechanical properties like strength and toughness. First one, we have rolling. In this process, the workpiece in the form of slab or plate is compressed between the two rotating rolls in the thickness direction so that the thickness is reduced. The rotating rolls draw the slab into the gap and compresses it. The final product is in the form of sheet. In rolling, a slab or plate is passed between the two rotating rolls, and the rolls compresses the metal in thickness direction, reducing the thickness while increasing the length. And then the rolls continuously draw the metal inward, producing sheets or plates with uniform geometry. And then rolling is one of the most widely used industrial forming processes, especially for steel production. Next, we have forging. The workpiece is compressed between the two dies containing shape contours. The die shapes are imparted into the final part. Forging compresses a heated metal workpiece between two shaped dies. The contour of the dies is transferred to the metal, forming the required geometry. And it produces very strong opponents because the internal grain flow follows the part shapes. And forging, it is used for critical parts such as gears, crankshafts, bolts, and tools. Third one, we have extrusion. and extrusion, the workpiece is compressed or pushed into the die opening to take the shape of the die hole as its cross-section. So, sa extrusion, yung heated metal billet is pushed through a die opening using a ramp, and then yung metal dumadaloy and it takes the shape of the die, forming the long uniform cross-section parts. And then it can also be done in hot or cold. And in hot extrusion, it reduces the force and it improves the ductility. We have the last one, which is wire drawing. It is similar to extrusion, except the workpiece is pulled through the die opening to take the cross section. Wire drawing pulls a metal rod through a tapered die, reducing its diameter and increasing its length. Unlike extrusion, yung sabi ko kanina, yung heated metal billet is pushed through a die opening using a ramp, and drawing pulls the metal and it produces wires for electrical applications, cables, springs, and fasteners. And usually it is performed in cold to achieve good surface finish and dimensional accuracy.
To discuss the classification of basic sheet metal forming. So what is sheet metal forming? So this is a process of shaping and cutting flat metal sheets using powerful tools like punches and dies. In this process, the metal can be bent to form angles, stretched into deep shapes like cups or containers, or cut cleanly in straight lines. So there are three major categories of sheet metal processes: the bending, deep drawing, and shearing. The first one is the bending. So bending operations are performed using punch and die tooling. The two common bending methods and associated tooling are V-bending, performed with V-die, and edge bending, performed with a wiping die. So in V-bending, the sheet metal is bent between a V-shaped punch and V-shaped na die. So included angles ranging from very obtuse to very acute can be made with V-dies. It is often performed on a press brake, and the associated V-dies are relatively simple and inexpensively. Next is the edge bending. So edge bending involves cantilever loading of the sheet metal. A pressure pad is used to apply a force to hold the base of the part against a die. So while the wiping die force the part to yield and bend over the edge of the die. So this edge bending is limited to bends of 90 degrees or less. More complicated wiping dies can be designed for bend angles greater than 90 degrees because sa pressure pad, wiping dies are more complicated and costly kaysa sa V-dies and are generally used for high production work. Next is the deep drawing. So this operation used to make cup shape, box shape, or other complex curve and concave parts. So it is performed by placing a piece of sheet metal over sa die cavity and then ginapush siya ang metal into sa opening sa punch kani. Then, the blank must usually be held down flat against sa die by a block holder. Kani, mani ang blank. So, kaning blank must usually be held down flat against sa die by a block holder. So, the common parts na mabuhat sa deep drawing include beverage cans, sinks, cooking pots, and automobile body panels. So, last is the shearing. So this operation is a sheet metal cutting along a straight line between sa two cutting edges by means of a power shear. So, ang distance sa ato ang upper blade and the lower blade is known as the clearance or the blade clearance. So, it is crucial for achieving high quality cuts and extending the lifespan of the blades. And that's all. Thank you.
Today, I will be discussing working temperature in metal forming. It includes cold working, warm working, and hot working. Understanding how temperature affects the metal behavior is important because it determines how easily the metal can be shaped, how strong it becomes, and what kind of equipment is needed. So before tamo tackle sa 3 different working temperatures, we must first understand kung unsa ang working temperature. So sa PPT, the definition of working temperature is the temperature range where a metal can be shaped and its microstructure adapts to achieve desired properties. Different temperatures change the structure and properties of the metal. So tungod ani, there are metals that may become softer, stronger, harder, or even flexible depending on how hot or cold they are when they are shaped. So para ma-compare nato ang klase-klase na temperatures, ginagamit nato ang melting temperature, or also known as TM. So TM is the temperature where a metal starts transitioning from solid to liquid. It serves as a reference point to understand how close or far the forming process is from fully melting the metal. So based on how close the working temperature is to TM, metal forming processes are divided into 3 categories: cold working, warm working, and hot working. So the first working temperature is a cold working. So cold working is done at or near room temperature, and it is performed below the metal's recrystallization temperature. So wala may heat applied, the metal remains strong and stiff while being shaped. So also said, sa cold working, there is a process called strain hardening nga may tabo. So strain hardening happens when the metal is forced to deform, causing tiny internal deflects called dislocations to multiply. So as more dislocations form, they start blocking each other. So mura na siya traffic jam inside sa metal. So this blockage makes movement harder, causing the metal to become stronger and harder, but also less flexible and more likely to crack. The second one is the warm working. Warm working takes place between room temperature and the recrystallization temperature. So at this temperature, the metal becomes easier to form compared to cold working, but it is still not soft enough to behave like hot work metal. Warm working gives a balance. The metal is softer and more formable than in cold working, but still strong enough to maintain structure. So this makes it ideal for processes requiring moderate shaping with controlled heat. So the third one is hot working. Hot working occurs above the recrystallization temperature, but still below the melting temperature. So at this range, the metal becomes very soft, making deformation easier. So unlike cold working, strain hardening does not happen in hot working, because new grains continuously form as the metal is being shaped. So this keeps the metal soft during the process, allowing very large deformation without cracking. As you can see guys, there are values na makita ninyo sa PPT, which are the 0.3, 0.5 to 0.75. So kanina mga value will help us identify whether the working temperature of the metal is warm working or hot working. Moving on, I'm going to discuss to you the advantages of cold working. The first one is closer tolerances can be achieved. So in cold working, the metal doesn't expand or shrink because there's no heat involved. So that's why we can achieve very precise and accurate dimensions. Number 2 is good surface finish. So since the metal stays at room temperature, oxidation does not form on the surface. This keeps the final product smooth and clean. So for the third one is the higher strength and hardness due to strain hardening. So as the metal is deformed at low temperature, dislocations multiply and lock up inside the structure. This naturally makes the part stronger and harder. The fourth one, grain flow gives desirable directional properties. When you deform the metal, the grains stretch in the direction of the applied force. This improves strength and performance in that direction. The fifth one is no heating is required, so furnace, fuel, and electricity costs are minimized. Because no furnaces or heating systems are needed, energy consumption stays low. This significantly reduces the production cost. The sixth one is minimum machining required. Cold work parts come out with accurate dimensions and smooth surfaces. That means only minimal finishing or machining is needed afterward. So now, I'm going to discuss about the disadvantages of cold working. The first one is higher forces and power are required. The metal is harder at room temperature, so machines must push harder to shape it. This means more power and stronger equipment are needed. So for the number 2, strain hardening limits the amount of forming. So as we continue working the metal, it becomes tougher and more brittle. At some point, it cannot be shaped further without cracking. So the third one is annealing cycles may be needed. When the metal becomes too hard, we have to hit it to soften. So the third one is annealing cycles may be needed. When the metal becomes too hard, we have to hit it to soften it again. So this slows the process and adds extra steps. The fourth one, some materials are not ductile enough. Brittle metals do not deform well at low temperatures. So instead of bending, they may crack or fracture. So for the advantages of warm working, the first one is improved plastic deformation behavior compared to cold working. At warm temperatures, the metal becomes more flexible and easier to shape. This reduces the risk of cracking during formation. Second one is lower forces required. So the slight temperature increases softens the metal. Because of that, machines don't need to apply as much as force. Third one is allows the formation of more complex shapes. Since the metal is more formable, we can create more complex shapes than in cold working. It offers a good balance between strength and formability. The fourth one is can reduce the need for annealing stages. So warm working lessens strain hardening. So the metal does not harden too quickly. This means fewer annealing interruptions. So in the advantages of hot working, the first one is allow significant plastic deformation. Once the metal is heated above its recrystallization temperature, it becomes extremely soft. So this allows dramatic changes in shape without cracking. The second one is enable large changes in workpiece shape. The metal can be stretched, bent, or compressed easily. This makes hot working ideal for producing large or complex components. The third one is requires lower forming forces compared to cold working. At high temperatures, metal resistance drops. That's why forming machines don't need to exert very high forces. The fourth one is can be used to form materials that would otherwise fracture at low temperature. Some metals that easily crack when cold become ductile when heated. This lets them be shaped safely in hot working. The fifth one is there is no strengthening from work hardening during the process. New grains form continuously while the metal is being worked. This keeps the metal soft and workable throughout the process. So moving on to the disadvantages, the first one is tools have a shorter lifespan due to a high temperature exposure. Tools are constantly exposed to high heat, which weakens and wears them out faster. This increases replacement and maintenance costs. The second one is the surface finish is usually poorer. When metal is hot, it reacts with oxygen and forms scale. This scale roughens the surface and often needs to be removed later. The third one is dimensional accuracy is lower. Hot metal expands and then shrinks as it cools. Because of this, it's harder to control the exact final size. The fourth one is the oxidation can occur on the workpiece surface. The fourth one is oxidation can occur on the workpiece surface. High temperatures promote oxidation on the surface of the metal. This creates scale that must be cleaned off before finishing. So that's it for my report, no? So in summary, the choices between cold, warm, and hot working depends on the size, required strength, accuracy, cost, and purpose of the metal product. Cold working provides precision and strength. Warm working offers a balance between force and formability, while hot working makes large deformation easy but requires more energy and results in rougher surfaces. So that's it for my report, and thank you for listening.
Good day everyone. So today I'm going to discuss about foundry operations. So first, what exactly is a foundry? So a foundry is a place where solid metals are melted and shaped into different products. These metal parts are used almost everywhere, like in cars, airplanes, buildings, and machinery. Basically, the foundry takes a solid metal, melts it, and forms it into a specific shape using molds. The whole goal is to produce parts that are accurate, durable, and fit exactly what industries needs. Next, let's look at the casting process. It goes through several important steps. First, the metal undergoes melting and degassing, where it is heated until it becomes liquid and impurities are removed to ensure quality. Next, let's look at the casting process. It goes through several important steps. So first, the metal undergoes melting and degassing, where it is heated until it becomes liquid and impurities are removed to ensure quality. Next, mold creation occurs, preparing a mold based on the desired shape of the final product. The liquid metal is then carefully poured into the mold, followed by solidification and cooling as the metal cools and hardens. After cooling, the mold is broken during shakeout and cleaning, and the casting is cleaned of any remaining mold material. Finally, the casting undergoes finishing and inspection, where any rough areas are smoothed, and the casting is checked for defects to ensure it meets the required standards. Each step is important because skipping or rushing any of them can affect the quality of the final product. Melting is one of the most important stages because everything starts here. In this step, the metal is heated to the right temperature so it fully melts and flows smoothly. To achieve the best results, several important factors must be carefully controlled, including the correct melting temperature, maintaining consistent heat inside the furnace, and considering the specific type of metal or alloy being used. Proper melting ensures the quality and strength of the final product, making this step essential for successful casting. So foundries use different types of furnaces depending on the type and amount of metal. So, example, induction furnaces, it melts metal using electricity. It is efficient and offer precise temperature control, making them ideal when accuracy is crucial. Okay, next example is electric arc furnaces. So it melts metal using a very hot electric spark and can reach extremely high temperatures, making them suitable for metals like steel. And the last one is cupola furnaces. So it is more a traditional option where metal is melted by burning fuel right next to it. It is commonly used for melting iron due to their capacity and cost effectiveness. So the type of furnace affects the time, temperature, energy use, and even the quality of the final casting. Another crucial step in ensuring the quality of the cast metal is degassing, a process that removes dissolved hydrogen from the molten metal. If this hydrogen isn't removed, it can lead to porosity or tiny holes inside the casting, which significantly weakens the final product. By effectively degassing the molten metal, we can achieve notable improvements in strength, making the casting more resistant to stress, flexibility, allowing the metal to bend without fracturing, surface finish, resulting in a smoother appearance and overall quality, ensuring consistent mechanical properties throughout the casting. To make sure the melted metal is clean and strong, different methods are used to remove unwanted gases. So here are some examples. First is vacuum degassing. It lowers the air pressure to get rid of gases. It is good for removing gases like hydrogen from the melted metal, which can cause problems in the final product. Next is rotary degassing. It uses a spinning part to mix a gas into the melted metal and push out hydrogen. The spinning helps the gas grab the hydrogen so it can be removed from the melted metal. And last is the high shear melt conditioning or HSMC. It uses strong mixing to make the melted metal better. It is often used for aluminum because it mixes the melted metal well, making it smoother and less porous. So each method has its own advantages, but the main goal is always to keep the molten metal clean and free from gas. So that's the end of my discussion. Thank you.
Let's start with some specialized casting methods that rely on unique mold materials or techniques. Closed foam casting. This method uses a polystyrene pattern, essentially a foam-loaded foam model of the final part, which is then surrounded by a mixture of ceramic and sand. When the molten metal is poured in, the heat vaporizes the foam, allowing the metal to fill the excess space and pattern occupied. It's a clean, single-use process. Pre-process casting. This is a newer environmental friendly method. It uses vacuum pressure and thin thermoform plastic sheets to hold the dry and bonded sand mold together. The advantage here is that no moisture, clay, or chemical resins are required to bind the sand. Belay ingot casting. This is the fundamental process. A belay is simply a basic, often rectangular or cylindrical shape of metal produced using a simple mold. These are not final parts but rather semi-finished product ingots that are typically used as the raw material for other fabrication processes like rolling or forging. Next, we move to a few more common and precision-focused casting methods. Sand casting. This is perhaps the oldest and most widely used method. It involves pouring molten metal into a mold made of green or resin-bonded sand. While versatile and inexpensive, it generally produces parts with rougher surface. Next, ceramic mold casting. Similar to sand, but using a finer material, a plaster mold, which allows for more intricate shapes and a better surface finish than traditional sand casting. Next, die casting. In contrast to consumable molds, die casting uses a permanent metal mold, often called a die. Molten metal is forced into the die cavity under high pressure. This process is excellent for high volume production and offer a great precision and surface quality. Next, investment casting, also known as the lost wax process. This is highly precise method. It uses a wax or similar sacrificial pattern which is coated in a ceramic slurry. Once the ceramic hardens, the wax is melted and drained out, leaving a perfect ceramic mold it uses for complex high tolerance parts. Powder metallurgy is a modern way of producing metal parts by blending elements or metal powders together to achieve the desired composition. The key steps are the powders are compacted in a die and then heated in a sintering furnace to bond the particles without fully melting them. The entire process sequence is blending, mixing, pressing, and sintering. The key advantage of powder metallurgy, the main strength of powder metallurgy is its ability to fabricate metals that are difficult to shape by other methods, especially high melting point metals or unique alloys. A perfect example is the forming of tungsten filaments for incandescent light bulb, which would be extremely difficult using traditional casting or machining. Finally, let's summarize the significant advantage that make powder metallurgy a valuable technique. First, it can be used to make parts that are very difficult to machines, like gears, very accurately. Next, the resulting surface is often very smooth and shiny, minimizing the need for subsequent healing or finishing work. Third, it requires relatively low processing temperature compared to melting metals, which save energy. Fourth, it produces a uniform microstructure in the material, leading to consistent material properties throughout the part. Fifth, there is no waste in this process. All materials are used efficiently, making it a very sustainable method.
Good day, everyone. I am the next reporter. I'm Clint Leonard A. Sanchez, and today I'll discuss what metallic foams are, how they are made, their properties, and their engineering applications. These materials are lightweight but strong, making them useful in many industries. What are metallic foam? Mostly made from aluminum, but titanium and tantalum can also be used, known for a high strength-to-weight ratio. Cellular structures are made of metal, not polymers. Uses: soundproofing in vehicle, crash protection, heat sink in electronics. Metal foams are usually made from aluminum because it is light and easy to work with, but other metals can also be used. They are known for their excellent strength-to-weight ratio, meaning they remain strong even if they are very light. These foams have a cellular or sponge-like structure, but unlike regular foams made of plastic, this one is made of metal because of this structure. They are commonly used for soundproofing in vehicles, absorbing impact during crashes, and managing heat in electronics through heat sinks. Now let's move on how metal foams are made. Production method. Gas bubbles are created inside molten metal. Metal viscosity is increased using ceramic powders or alloying elements. Foaming methods. Injecting gas into liquid metal. 2. Precipitating dissolved gas. 3. Using gas-releasing blowing agents. When metal is melted, gas can be introduced into the liquid to form bubbles. These bubbles naturally want to float to the surface because of the buoyancy. To stop them from escaping, the molten metal must become thicker or more viscous. This is achieved by adding ceramic powder or special alloying elements that holds the bubbles in place. Once the metal is cool and solidified, it forms a porous foam structure. There are three main methods to create foam in molten metal. First, gas can be injected directly. Second, gas already dissolved in the melt can be forced to come out. Third, chemically cooled blowing agents can be added, which release gas inside the melt and form bubbles. All three methods result in a porous metal foam when the material solidifies. The key properties of metallic foams. Very light. 75 to 95% of its volume is void space. Very high porosity. High compressive strength with good energy absorption. Low thermal conductivity and high strength. Metal foams are extremely light since most of their volume is empty space. Their high porosity makes them effective at absorbing energy impact. They can withstand compression well, which is helpful in crash protection. They also have low thermal conductivity, meaning they don't transfer heat easily. Despite being light and porous, they still maintain high mechanical strength. The engineering applications. The closed cell foam applications. Structural part requiring load-bearing capacity. Vehicle components for weight reduction. Impact-absorbing structures. Automotive frames with fewer parts, meaning lower cost, better performance. High-capacity impact energy absorber. Closed cell foams have sealed pores, making them stronger and capable of supporting heavier loads. Because they are lightweight and good at absorbing impact, they are used in vehicle frames to improve safety and reduce overall weight. This helps improve fuel efficiency and vehicle performance. Now let's move on to open cell foam applications. Vibration and sound absorption, filtration and catalysis at high temperature, heat exchangers, medical devices. The functional uses are filtration, damping, and flow control. Open cell foams have connected pores, allowing air or fluid to move through them. This makes them ideal for vibration and sound control. They are also used in filtration systems and catalytic converters, especially at high temperatures. Because fluid can pass through easily, they are good for heat exchanger. Their porous structure also makes them useful in medical devices like bone implant. Advantages of metallic foams. Much lighter than solid metals, absorb high amount of energy, excellent sound and vibration damping, high temperature stability for titanium and tantalum foams, better durability than ceramic armor inserts, and last, can reduce part count in vehicles, cheaper manufacturing. Metal foams offer several advantages. They are much lighter than solid metals and can absorb large amount of impact energy, making them effective for protection and crash-related application. Their porous structure provides strong sound and vibration damping, while titanium and tantalum foams maintain stability at high temperature. They are also more durable than ceramic armor inserts, which can crack easily, and they allow manufacturers to reduce the number of parts in vehicles, lowering production costs and improving performance. To summarize, metallic foams are lightweight but strong materials with excellent structural and functional properties. They are used in vehicles, electronics, filtration, medical devices, and even protective armor. The unique combination of low weight strength and energy absorption makes them increasingly important in modern engineering. Thank you so much for listening. This is the end of our report.